Hello. In this video, we are going to cover theoretical probabilities. I will warn you, this video is very definition heavy. All right, let's get started. Probabilities are measured as fractions, decimals, or percentages. So because of that, you could see probabilities described as 1/2. You could see a probability described as 0.5, or you could see a probability described as 50%. All of these are possibilities when working on probability problems. If an event never happens, then the probability is 0. If an event always happens, then the probability is 1. Okay, so probabilities are between 0 and 1. The probability of an event not happening is 1 minus the probability it will happen. So we call this the complement of the probability. Or sorry, complement of the event. So for example, the probability of rolling a 1 on a dice is 1 in 6, or 1/6. The probability of not rolling a 1 is going to be 5/6. And you can just check that out, right? So the opposite of rolling a 1 is going to be not rolling a 1. Not rolling a 1 would be rolling a 2, a 3, a 4, a 5, or 6. There's 5 possibilities out of 6 total. Okay. So when we talk about events that we're finding the probability of, we typically describe them with uppercase letters. You'll see A, B, C. Those are usually the ones that we work with first. So to give an example, we would go through and we would say, let A represent it rains tomorrow. Then we would go through and use symbolically. If we say P of A, that would mean probability that it rains tomorrow. And if we went through and said P of A equals 0.50, then this translates as the probability it will rain tomorrow is 50%. Okay. So we can go through and summarize this, and we'll do this throughout as we go through and come up with more and more definitions. I will summarize them occasionally. So let's just summarize what we've got so far. Given event A, we'll call it rule 1. Probability of event A is between 0 and 1. Okay. You cannot have probability below 0, and you cannot have a probability above 1. The probability A does not occur equals 1 minus the probability that A occurs. We can use A complement to represent A does not occur. And that if you use that notation, then the probability of A complement equals 1 minus the probability of A. And so we get to this simple formula. Okay, moving on, more definitions. All right, next, sample space. This is the list of all possible outcomes of an event. And we typically use capital letter S. So some examples of sample spaces. If you had the roll of a dice, or dice, the sample space would equal 1, 2, 3, 4, 5, 6, because those are the possible results when you roll a dice. For a coin, sample space, heads or tails. Okay, and so that's the idea. All right, we've been using the term event, but we're going to now strictly define it. Event is a collection of possible outcomes from the sample space. So we could say event A equals, say, 1, 3, and 5 for a dice roll. So odds. Right? So you can have more than one possible result from the sample space in your event. So the event doesn't have to be just roll a 1 or roll a 3. It could be roll a 1, 3, or a 5, roll an odd. Or it could be roll a 2 or a 4 or a 6, roll an even. Or it could be a mix of those. You could go through and have an event that is 1, 2, and 5. So all of these are possible example events that you could have. So there's no restriction. The event could be roll 1, 2, 3, 4, 5, or 6. Could be everything that's in the sample space. And then the probability of that event would be 1, as we discussed, because you're guaranteed to get one of those results. All right, so now we're going to add another event, another rule. Assuming outcomes are equally likely. Rule 3 is the probability of an event equals the number of outcomes in the event divided by the number of outcomes in the sample space. Again, that requires that all of the outcomes are equally likely. That does not work if the outcomes, if the outcomes are not equally likely. So that would work with dice or coins because the outcomes are equally likely. All right, there's another example here. So suppose 30 people are in a class and a person at random is selected to win a prize. Person at random is selected to win a prize. What is the probability that any single individual wins the prize? Well, if the individual wins a prize, so if I'm in that class and I win the prize, there's only one of me that's in the event space. The one person wins the prize. And then there's how many people in the sample space? Well, if the class has 30 people, then there's 30 people in the sample space. So the probability would be 1 out of 30. For completeness, the probability of getting something in the sample space would be the number of outcomes in the sample space divided by, so, okay, I have to explain this. I think it's a little less obvious than when I wrote it down in my notes. The idea is what we're doing is we're using the the result on the previous page as a formula, and then we're plugging S in. All right, so the idea is that if you take rule 3 here, this is the probability of A, and you put A in. Now, the idea is that if you put S in, then you'd have the probability of getting something in the sample space would equal the number of outcomes in S, because if you're substituting S in for A, you'd put S here. So you'd get the number of outcomes in S over the number of outcomes in S, and then you've got the same thing on the numerator and the denominator, and you get 1. So the probability of getting something in the sample space is 1. So that's just kind of for completeness. It's kind of obvious. All right, so let's look at another example. Suppose a bowl contains 5 red die, 3 green die, and 2 white die. Oops, this would be 3 green. And 2 white die. What is the probability of drawing a red die? What is the probability of drawing a green die? And what is the probability of drawing a white die? All right, so probability of drawing a red die. So I think about how many things are in the sample space. So if you went through and numbered the red die, the red die number 1, red die number 2, red die number 3, number 4, number 5. And so in the event space, there are 5, count them, 5 red die. And then the sample space has 10 total die. And so you get 5 over 10 or 1/2. The probability of a green die, again, so the same thing, if you numbered these green die, green die, number 1, green die number 2, and green die number 3, there's 3 possible ways that you could get a green die. So there's there's 3 green die in the event space of drawing a green die, and then there's 10 total die. So you get 3/10. And then the probability of a white die, there's 2 white die, so you get the idea. 2 out of 10 introduces to 1/5. All right, let's look at another example. Roll 2 dice and add the outcome. And by add the outcome, it means add the number of pips. Those are the little dots that are on the dice. Outcomes, I think is fine, plural, yeah, because there's 2 dice. What's the probability that the sum is 7? Okay, so this one is a little bit complicated. So if you go through and think, all right, well, if I go through and I roll 2 dice and I can get from 1 to 6 on each, then my outcomes, so possible outcomes, are going to be 2, 3, 4, through 10, 11, and 12, right? So you're adding what's visible on the dice. So you could have the smallest thing you could get would be 2 single pips, for 2, and then the highest you could get 6 pips on each, and then you get 12. So these are the outcomes. However, this is a great example of a situation where the outcomes are not equally likely. So there's only one way to get 2, which is a single pip on each dice. There's actually 2 ways that you can get 3. You can get 1 on the first die and 2 on the second, or you could get 2 on the first die and 1 on the second. And so these events are not equally likely. All right, so that's critical, for going through and calculating the probability. If they were equally likely, then you could go through and just say, all right, well, 7 is one of the possibilities, and there's 2 through 12, so there's 10 of those. So you go through and take 7 divided by 12, and you're good, and that's the answer. But unfortunately, you can't do that because the events are not equally likely. Since the events are not equally likely, the outcomes are not equally likely like this, what you really need to do is you need to go through and create the sample space to identify how many different possible results there are. And then you need to calculate the event space and then calculate how many different ways you can achieve the event. And then you can put the 2 together. So this is a common way that you have to go through and calculate probabilities, assuming the outcomes are not equally likely. If these were equally likely, it would be easy. Unfortunately, it's not like that. All right, so we want to go through and calculate the sample space. So what are the different possible results? Well, what we're going to do is we're going to represent them with parentheses. You don't have to represent them with parentheses. There's lots of different ways you can go through and represent them, but that's just one way to do it. So you could roll 1 and 1. You could roll 1 and 2. You could roll 1 and 3. You could roll 1 and 6. You could roll 2 and 1. You could roll 2 and 2. You could roll 2 and 3. You could roll 2 and 6. You could roll, let's see, we got 1, 2. So let's do 5 and 1. You could roll 5 and 1. You could roll 6 and 1. You could roll 5 and 2. 5 and 3. 5 and 6. 6 and 2. 6 and 3. 6 and 6. All right, and so we get our little, obviously I didn't write every single element here. You don't have to write them all, but we can figure out how big this is, right? So how many rows are there? So we've got 1, 2, 3, and then I put this dot, dot, dot. There's 4, 5, 6. There's 6 total here. So we have 6 possible rows. How many columns? We've got 1, 2. Then I skipped a couple, 5, 6. So if you just count those 1, 2, 3, 4, 5, 6, there's 6. So the sample space is 6 by 6, which is 36 possibilities. Okay, and then the event space. Now that's going to be the ways that we can achieve a sum of 7. So looking at our event space here, how could we achieve a sum of 7? We could have a 1 and a 6, right? That sums to 7. We could have, so it's not visible here because I did a dot, 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 but 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. All right, so how many of those? There are 6 total in the event space. And so now, so the probability, if we go through and say our event space here, that this is A, the probability of A is equal to, and again, so what I'm doing here, if it's not obvious, is I'm using this formula, number of outcomes in A over the number of outcomes in S. So I'm just using the formula here. So the number of outcomes in A, there are 6 of them, over the number of total outcomes, which is 36. And so the probability of getting a 7 is 1 in 6. Okay, and so that's so this is a handy way to do it. So we did use that same technique here. We just didn't write out the sample space and the event space. We just kind of did it in our head. But this is just this example here. We're just kind of using it. We used it here. Well, we're using it here. It's a common way to go through and calculate probabilities. that's not all. All right, so moving on, combining events. It's like a subsection here. All right, so more complex events can be created by using and or to combine events. All right, so to introduce this idea, let's take a look at a picture. All right, so what we have here is we have a picture of some people, and we're looking at two different things that are, that we're going to measure as being different between these people. So we're looking at hats and sunglasses. All right. There we go. All right. And so you could go through and do the probability that someone is wearing a hat. So you can see there's 1, 2, 3 hats. So that's something that we could do, and that, with what we've covered so far. You could go through and calculate the probability that someone is wearing sunglasses. All right, so we've got 1, 2, 3, 4 sunglasses. All right, so that's something that we could do. However, what we want to introduce is the idea that a person, we want to introduce the idea of combining those two. So I was going to jump over back to the whiteboard, but I think we've got enough from here. So let's just write probability that someone is wearing a hat. So we just said that. That's 3 out of 6. We have probability someone is wearing sunglasses. That is 4 out of 6. Right. And now what we want to introduce is the idea of what is the probability that someone is wearing a hat and glasses. Actually, hold on, I'm going to rewrite that. So what we do here, maybe just to try and make it a little bit clear that this, the importance of this is actually write it in all caps. And so a hat and glasses. So how many people have a hat and glasses on? So this person has a hat, but no glasses. This person has sunglasses, but no hat. Here we've got a hat and sunglasses. Oh, I forgot the little caption here tells us that the people raising their hands have hats and sunglasses on. So anyway, so there's 2 people. And so there's 2 people in the event. That's the event. And there's 6 in the sample space. So 2 out of 6 is the probability that someone is wearing glasses and a hat. Okay, so that's one way in which you can go through and do an and to create a more complicated event. So, with just our simple events that we've covered up to this point, hat, glasses, now we can combine them by doing and, so we can check to see, when both of these criteria are met. Let's look at another example where we can do something like that. So here we have a table. This table just describes education and marital status for 665 randomly selected residents. It's right there at the bottom. So we can go through and do the probability. We can do probabilities here. So let's say we're looking at the probability that a person is married. Actually, let's just do this, shorthand this. So married. All right, so if you're going to calculate the probability that a person is married, what we need to do is we need to figure out all of the people in this space and all the people in the space that are married. So how many people are in the space that are married? To calculate that, you'd want to have this number here, 408. So 70 people are married, have less than high school, 240 high school, 98 college or higher, 408 total married. And then how many total people are there in the sample space? 665. All right. So if you're asked to go through and calculate the probability that people are married, you need to find all the married people and put them over all the people in the sample space. We could do another possibility, the probability that someone has college education or higher. So how many people are of college education or higher? Let me fix that P. It's bugging me. All right, so college or higher. So we've got 27, 98, 15, 3. We have 143 total that are college educated. Out of how many are in the space? 665. Okay. Now, what if we wanted to go through and do the probability that someone is married and has a college education or higher? All right, so if we look through the table here, where are the people that are married and have college education or higher? So they have to be in the married column and the college education or higher column. So that's just going to be that 98 right there. And how many people are in the sample space? 665. Okay, so there's a couple examples with and. Now let's talk about examples with or. First, real quick before we get into or. So one of the things that we're going to look at, because this one thing that we're going to do is we're going to calculate the inclusive or. So when it comes to or in statistics, you're using what's called the inclusive or. What does that mean? So what that means is it means that if you have two criteria, then you can satisfy one criteria or the other criteria or both of the criteria. So there's such a thing as an exclusive or, where if you were looking at two criteria, it would be one or the other, but not both. Okay, so we use the inclusive or. So given two criteria, the inclusive or is satisfied. Means one criteria or the other criteria or both. The criteria are met. And again, the difference is there's a such thing as an exclusive or. Given an exclusive or, if you had two criteria, it would mean that one criteria or the other criteria is satisfied, but not both. Okay, so that's the difference. A little technical there, but that's how it works. All right, so let's do some examples with or. Hold on just a second. Let's jump back to our picture here. We have the probability of a hat and glasses. What about the probability of a hat or glasses? Okay, so when we're calculating this, what that means is that if someone has a hat, then they count. If someone has glasses, then they count. And if someone has a hat and glasses, then they also count, right? The inclusive or. All right, so we take a look. We've got glasses. That meets the criteria. That's 1. Hat, that's 2. Hat and, that's 3. Glasses, 4. Nothing, neither hat nor glasses. So that person does not count. And then hat and glasses, 5. So we got hat or glasses. That's going to be 5 out of 6 total possibilities. There's one person who does not have on a hat or glasses. All right, let's jump back over to this guy. All right, so we're kind of out of space here. Let's see, I'm gonna drag more, make more space. Let's say we wanted to go through and calculate the probability of married, what should I do in my notes here? Single or married. Okay. So I didn't do what I expected, which is married or college. Maybe coming back to that. So single or married. So what we want to look at, so single, we have 112 people are single. And then married, we have 408. And then there's 665 total. And so if you add those up, we get 520 over 665. Okay. Okay, yeah, and then the second one I did was married or college. All right. There's a method here. All right, so we've got married or college. So if we take a look at this, we've got, here's our married column, right? So we've got 408. Or college, so here's our college column, that's 143. However, if you look at this, we went through and we counted 408, that included this 98, and then we counted 143, that included this 98. So we counted that 98 twice. So what we want to do is we want to subtract off that 98 that we counted twice. So now we're still counting it, we're just counting it once. And then you've got to do the math there. It's 453 out of 665. Okay, so why did I end up doing it like that, where I did 2 different examples? The reason is that there's something different in those 2, clearly, right? So in this case, we went through and just ended up adding 2 things together to get the number that's in the numerator. Whereas in this case, we ended up adding and then subtracting. So there's two different situations that are going on here. And that's going to be our next topic of discussion. So one of them is where we have like the single and married. You can't be single and married. You can only be one of the two. All right. So since it's not possible to be both of these things at the same time, whereas you can be married and in college. And so because of that, we have got to do something different. So this case where you have single and married, where you cannot be in both, that's called mutually exclusive. So we're going to spend a few minutes talking about that. All right, so mutually exclusive. So events are mutually exclusive when there's no overlap between the events. All right, so let's go back to that last example and discuss other things that would be mutually exclusive. Because if we look at this, when it comes to a table like this, mutually exclusive is kind of obvious, when you know what to look for. All right, so what are examples of things that are mutually exclusive in this table? So we said single and married are mutually exclusive. The way that the table is set up here, divorced, so you can't be single and be divorced. So none of the divorced people, these 84 people, none of them are counted over here under single. They are separated. You can't be a widower or be widowed, and also be married at the same time. So basically, when you know what to look for, everything that's in the columns is mutually exclusive. So single is mutually exclusive from divorced, married from divorced, widowed from any of those others. So these are all the things that are mutually exclusive. Meanwhile, can you have less than high school and high school at the same time? No, you can't. So these are counted separately. So none of these 17 are in the 68. And so what we've got here is that you've got the rows also represent mutually exclusive. So if you were to go through and find the probability that someone has less than high school and high school, you would just end up adding these two together. We wouldn't need to go through and do that subtraction stuff. So the subtraction stuff, that's what you have to do when you have events that are not mutually exclusive. Okay, so mutually exclusive, it's very easy to go through and do the calculations. So we're going to have a rule for that. Add to our rule list. Rule 4. Probability of event A or event B. So two events equals the probability of A plus the probability of B. So this assumes this is mutually exclusive when they're mutually exclusive. All right. If they're not mutually exclusive, what do we need to do if they're not mutually exclusive? Well, we did it on that previous problem. We went through and found the probability of event A or event B. What did we do when we found that? We could go back and take a look. So when we calculated that probability, what did we do? So when we found the probability of college or married, we went through and took all the married people, add them up. We took all the college people, add them up, and then we subtracted the overlap. What was the overlap? The overlap were the people who were married and were in college. So we subtracted the and so that's going to be represented in our formula. All right, so the probability of event A or event B, assuming they are not mutually exclusive, you do probability of event A plus probability of event B minus the probability of event A and B. All right, so this is not mutually exclusive. All right, so let's do some examples. So let's say you roll a 6-sided die. We want to go through and we want to find the probability that you get an even number or a number greater than 4. And then B, find the probability that you get an even number or the number 5. All right, so the first one, what we want to do is we want to go through and find the probability of an even number or greater than 4. So you have to think about, are those mutually exclusive? Can you have an even number that is greater than 4? Is there anything that's in both of those two at the same time? If so, then we want to use the second formula, this formula. Meanwhile, if they are mutually exclusive, if you cannot be even and be greater than 4, then we can use the easier formula, the second or the first formula. All right. In this case, if you sit down and think about it, or if you just list out the possibilities, you will discover that there is an even number that is greater than 4. And so these are not mutually exclusive. And so what we need to do is we need to do the probability of an even plus the probability of greater than 4 minus the probability of even and greater than 4. And so if we think about those, so what are the even numbers? When it comes to 6-sided dice, what's going to be in the event space? So we're going to have 2, 4, and 6. There's 3 possibilities. So that's 3 out of 6. What is the probability that we get greater than 4? What are the numbers that are greater than 4? So it doesn't say greater than or equal to, it just says greater than. So 5 and 6. So there's 2 possibilities in the event space out of 6 total. And then what are the even numbers that are greater than 4? So 6, we ended up counting twice in both of the 2 events. And so we need to subtract off that 6. And so one of them. And so if we do that, you're going to get 4 out of 6, which reduces to 2/3. All right, so that's for part A. And then for part B, we want to find the probability that we get even or 5. All right, so again, we need to check, can you be even and be 5? Are they mutually exclusive or not? I would say, no, you can't, 5 is not an even, it's an odd. And so since these things are mutually exclusive because you cannot be in both piles at the same time, that means you can calculate the probability by just taking the two and adding them. So what is the probability of getting an even? We've already covered that. That's 3 out of 6. What's the probability of getting a 5? That's 1 out of 6. So we also get 4 out of 6, just 2/3. Or reduced to 2/3. Okay, we got another example here. All right, so we've got a picture that has some data on it. Okay, so what we've got on this picture is that the height of the bars indicate the percentage of the posts in each category. All right, so this is 29. So, okay, so I apologize. I did not make clear what this is. So what this is someone went through Facebook, identified science-related Facebook pages, and then they looked at the posts. So these are posts from science Facebook pages. And in particular, what these represent is they represent the topic of the post. So the post was either about discoveries, or it was about applications, or there were posts that were about advertisements, or there were posts that were explanations or responses, reposts. That there were some posts that were not related to science at all on the Facebook, or then there was just a catch-all. All right, and so the question is, what is the probability that a post is an advertisement, is not related to science, or falls into the other category? So advertisement, non-science, or other. Okay, and so what we can do if we were to write these out, so probability, we've got advertisement or non-science. I'm gonna run out of space because I'm writing too big, or other. Let's go ahead and make this a little bit bigger. So are these mutually exclusive? So that's a good question. Could advertisements also, in the advertisement, could they cover discoveries? The thing is the way that you can tell that they're not mutually exclusive, if you add up all these percentages, they add up to 100%. So because they add up to 100%, that tells us that they are mutually exclusive, that nothing in this pile is in this pile. If not for that, then you might have to go through and read the description here. You might have to ask some questions to determine whether that were the case or not. So just for example, if instead of these being percentages, let's say they were just counts. All right, so someone went through and just counted, and this represented, instead of 29 here, let's say they're 513 discovery posts, 275 application posts. If someone had just given you a list of the number of posts, you would not be able to tell whether they were mutually exclusive. You could have things that were counted multiple times. And so it's important to look for that type of information if you're going to go through and be doing calculations. However, since these add up to 100%, we're told they're percentages and they add up to 100%, we can tell that they are mutually exclusive. So we could find this by just finding the probability of an advertisement plus the probability of non-science plus the probability of other. So since they are mutually exclusive, we can just add them up. And so the probability for advertisements is 16%, non-science 5%, other 10%. And so if we go through and add those up, we get 31%. So 31% of the posts were not, really related to the topic of the Facebook page, which is science, right? An advertisement is really not related to, well, I guess it could be a science related advertisement, but I think it's implied that they were just kind of spam advertisements. And so the idea here is we're identifying what is the percentage of posts on science related websites that were not related to science. And it looks like it's almost a third, which is pretty high. Okay, that covers this topic. Thank you for watching, and I'll see you next time.